Okay, let's start talking about diagnostic testing, and specifically I'm going to talk about sensitivity and specificity. So a diagnostic test is a maneuver to rule in or out a diagnosis. It can be a question that you ask on the interview. It can be a physical exam. It can be a blood analysis, or it can be radiology, such as an X-ray. Or it can be a physiological challenge. So what's the purpose of it? The purpose of it is we have these thresholds, the test threshold and the treatment threshold. And so what this means is I can have a test threshold that says if the probability of you having this disease is less than this threshold, then no further analysis is needed. No treatment and no test. So no treatment, no test. And then you have the treatment threshold where the probability of you having the disease is so high that you need no more testing, you just treat it. So this is what we would call ruled out. You rule out a disease, and this would be called ruled in. But then we have this whole spectrum between here and here where the disease is neither ruled out nor ruled in, so we don't know whether or not to treat it. So suppose you have a 6-year-old with a fever, sore throat, exudate, cervical lymphadenopathy, and exposure to strep. So at this point, this is beyond the treatment threshold. You don't need any more testing. You just simply treat it because the probability that they have strep is so high. On the other hand, imagine that they had fever and sore throat only. None of these other symptoms. This is simply a cold. You don't need to treat it for strep. The probability that they have no strep, or just the probability that they have only a cold, is fairly high, and so no further testing is needed. You ruled out strep. Now imagine, however, that you have the same 6-year-old, fever and sore throat. They don't have an exudate or cervical lymphadenopathy, but they do have exposure to strep. At this point, they fall in this category. We need to do further testing. In that further testing, we'll either rule in or rule out, hopefully, strep, and we know whether or not to treat. The problem with testing is that you can have false tests. Some of them can be false negatives, and some of them can be false positives. A false negative says that you don't have the disease when you really do, and a false positive says you do have a disease when you really don't. So we need to know the characteristics of our test. How often will we get a false negative, and how often will we get a false positive? The measure of that is called the sensitivity and specificity. So here along the top edge I have the disease status, the true disease status. So whenever you see a 4x4 box like this, typically you can think of the top part as telling you what the truth is, and then the side is telling you what the test says. So when the test is positive and the person really does have a disease, that is called a true positive. When the test is positive but the person doesn't have the disease, that's called a false positive. And then again, if they test negative and they don't have the disease, that is called a true negative. And if they test negative but they do have the disease, that's called a false negative. So you may encounter a box like this, and sometimes the boxes are just simply labeled A, B, C, and D, where A represents the true negatives, A represents the true positives, B represents the false positives, C the false negatives, and D the true negatives. So here in this column, right in the first column, we have everybody with the disease. So let's say that we have 100 people with the disease and 100 people without. So my total down here is going to be 100 and 100. So 100 people have the disease, 90 of them test positive, 10 of them test negative. And then on the people that do not have the disease, we will say that 90 of them test negative and 10 of them test positive. It doesn't have to be 90, 90, 10, and 10. It could be 90, 10, 80, 20. So the boxes don't have to, these corners don't have to equal each other. But for simplicity, I've made it so that they do. And so we want to be able to describe our disease in terms of numbers. And so what we have is something called the sensitivity. And the sensitivity is basically, I want to know what percent of positive people test positive. So what percent of positive people, that would be the true positives over all positives, which is true positives plus false negatives. That tells me the percent of positive people that test positive with this test. So I'm asking, how sensitive is this specific test? So to plug in numbers, I would have 90 over 90 plus 10 equals 90% sensitivity. And then with specificity, what it's asking is specificity. What percent of negative people test negative? So for all of the negative people, these are all negatives, so I have false positives and true negatives. So I can describe all negative people as being true negatives plus false positives. And I want to know what percentage of these negative people will test negative. So that would be my true negatives divided by true negative plus false positive. So you can see from these two equations, the sensitivity is true positive. So it's sometimes called the true positive rate, which is kind of a misnomer because it only tells you the true positive rate in people that are positive. The specificity tells you the true negative rate in people that are negative. It does not tell you the true negative rate of the entire population. So it's kind of a misnomer. So here again, I would do my true negatives, 90 over 90 plus 10 equals 90%. So 90% of people with this test that are negative will also test negative. Now the correlation with that, so sensitivity has a correlation called the false negative rate. So sensitivity is known as the true positive rate, right? And then the correlate of that is the false negative rate. False negative rate is equal to false negatives over true positives plus false negatives. So you can see it has the same denominator as sensitivity. It's simply inverting which of these two is going to be the numerator. And you'll see from this that it will be 10 over 100 in our example. And so you'll see that sensitivity plus the false negative rate will always equal 1, or 100%. The inverse of the specificity is called the false positive rate. And it's going to take on the same numerator, so it's the true negatives plus false positives, but instead it's going to have the false positives as the numerator. And again, false positive rate plus specificity is equal to 100%. So let me recover from this. This column will give you the sensitivity and the false negative rate. So sensitivity and false negative rate. On the other hand, this other column will give you specificity and the false positive rate. So the mnemonic for these two are spin and snout. This is basically what specificity and sensitivity mean. So a highly specific test, when positive, rules in a disease. So specific, positive, rules in. And snout, standing for a sensitive test, so the S and the N, sensitive test, when negative, rules out a disease. So sensitive, negative, ruled out. I know what you must be thinking. If sensitivity is the true positive rate, then how does it rule out a disease? Let's take a look at how each of these is set up. So the sensitivity, again, is going to be the true positives over the true positives plus the false negatives. Now, for sensitivity to be high, that means that this number should be close to 1, to equaling 1. If it was perfect, it would equal 1. So let's just give it some numbers again. Let's say that this is 100, and this is 3. So then we would say that out of 103 people, 100 of them will be, when tested positive, if they are positive, they will test positive 100 out of 103 times. So what I'm saying is that my false negatives are really low. If my false negatives are low and I get a negative test, it means that it's probably not a false negative. It's probably not a false negative. Why? Because my false negative rate is low. So if it's not a false negative, then getting a negative test means that the person probably really is negative. But what happens on this highly sensitive test if the person tests positive? Well, then we have two possibilities. They could either be a true positive or a false positive. But our sensitivity doesn't tell us anything about how many false positives there are. We simply don't know. Suppose that the false positives, let's zoom in really quick and write some numbers in. Let's say that the false positives were 50 and the true negatives were also 50. So we have a very high false positive rate. In this case, getting a positive test on this highly sensitive, so it's highly sensitive, getting a positive test wouldn't tell us whether the person was really positive or not. Getting the negative test, however, would almost rule out the disease. Now let's take a look at a highly specific test. So in this test, 100 people who are negative tested negative, while 3 people who were negative tested positive. So my specificity is true negatives over true negatives plus false positives. And in this case, it's 100 over 103. And so what does this tell me? Spin, so highly specific tests rule in a disease when positive. And so what I'm saying is, if this is positive, if it's a positive test, then it's likely that it is a true positive. Why? Because my false positive rate is extremely low. If I test somebody who doesn't have the disease, it's not very likely, that they will test positive. That they will test positive if no disease. So if they do test positive, it's probably going to not be a false positive, meaning it probably will be a true positive. So with a high specificity, we're saying that the probability of getting this false positive is really low, so getting a positive will probably be a true positive. On the other hand, with a highly sensitive test, we're saying the probability of getting this false negative is really low, so if it is negative, it will probably be a true negative. Now here's the caveat. Usually by increasing either the sensitivity or the specificity, you are decreasing the other. So increasing sensitivity leads to decreased specificity most of the time, and vice versa is true. Now a good example of exactly why this is, we can imagine that you have a new car, and so in this new car, this is your new Batmobile, and in this new car you have just installed an alarm, and you have set this alarm to be very sensitive. So just the breeze blowing across this car can set it off. If the alarm doesn't go off, you can be assured that no one is breaking into your car. But if the alarm does go off, if it's a positive alarm, you really don't know, was it the breeze? Was it a cat running under your car? Was it somebody playing their radio too loud as they drove by? You don't know. So a negative test is almost surely negative, but a positive test, you just don't know. So on this graph, we're representing everything that can set off your car alarm that is not a burglar. And then here we're representing every possible way a burglar could set off your alarm. If you set the sensitivity so high that it will catch every burglar if it happens, then you will also catch an extremely high number of things that are not burglars will also set off your car alarm. So a high sensitivity will get you a high false positive rate, and you can assure yourself that having all of these things over here happen will not set off your alarm. So anything on this side, you can assure yourself that it's going to be a true negative, that there really is no burglar, because burglar activity stops right here. Due to your neighbors complaining about your car constantly going off, you change the sensitivity of the alarm a little bit higher, and whenever you do that, there's a lot of things that could have caused the alarm to go off for no reason at all that you have just completely ruled out. There's a small number of things that can still set it off that are not burglar activity. However, at the same time, there is a bunch of burglar activity, well, not a bunch, but there is some burglar activity that will not be detected by your car alarm. So these really crafty burglars that know how to ease their way into your car, they will still be able to get in and your alarm will not catch them. Your car's still going off a whole lot right here, your neighbors are still complaining, so you crank the sensitivity really low, and at this point, it's never going to have a false alarm. Anytime this alarm goes off, you know it's because bad guys are coming and trying to get into your car. But there's still quite a few bad guys that can get in without setting off the alarm. A whole bunch. These would be false negatives. The alarm's not going off and burglars are getting into your car. So this would be an example of a highly specific test. It's specific for only burglar activity. Only burglar activity will set this alarm off. This is an example of a highly sensitive test that it will go off anytime a burglar attacks, but it can also go off for a lot of other reasons. It's sensitive to a lot of activity. And so by adjusting the sensitivity and specificity of your car alarm, you have a trade-off. So increased specificity causes decreased sensitivity. So on this side, you have no false positives. All your positives are true positives. On this side, you have no false negatives. If the alarm's going off, there really is nothing wrong with the car. If the alarm is not going off, there's nothing wrong with your car. And so we have looked at this curve, and we've described a curve that has a lot of overlap, and we can either be very sensitive or we can be very specific. Now, how can we get the curves to spread apart? How can we say the disease is absent and the disease is present? How can we more easily identify those? Usually you cannot do that with the same test. But what can cause these things to spread more apart? First of all, increased technology, so a better test. In this case, we would want to install a camera on the car. And the camera would identify people coming close to it, and it would put a ring on your phone and allow you to view the camera through your smartphone. In which case you could personally identify if somebody was breaking into your car, press another button, and the alarm goes off. But there might be a chance where you're sleeping and you fall asleep on top of your phone, and in which case you could still get a few false positives. Not as many. You've separated the curve quite a bit. Another way is to increase training. Better training means better testing. So, for example, if you draw blood and you get a high potassium, most of the time a high potassium on a blood draw is due to an error in taking the blood. And so the more you train your phlebotomist and the better they get at drawing blood, the fewer high potassium draws you will have. And so ultimately the point of this is that you want to be able to separate these curves of false alarms and true alarms, and then be able to set your test to identify right down the middle when possible. So one last time really quick, we're going to look at sensitivity. Sensitivity is equal to the true positives over true positive plus false negative. Specificity. Specificity is equal to true negatives over true negatives plus false positives. So one way to think of this is the truth is always on top. True positives in the case of sensitivity, true negatives in the case of specificity. If you remember that the truth goes on top, you'll always know how to draw out these equations. Then your false positive rate is equal to 1 minus the specificity, which is also equal to the false positives over false positives plus true negatives. And the false negative rate is equal to 1 minus the sensitivity, which is equal to the false negatives over true positives plus false negatives. Another way to say this is that specificity plus the false positive rate equals 1, sensitivity plus the false negative rate equals 1. And if we want to make a digression to study analysis, so if we wanted to compare these to a study analysis where we had this truth on top and what we're looking at on the side, and you have A, B, C, and D, then the false positive rate, which would be B over B plus D, is equal to alpha. The false negative rate, which is C over A plus C, is equal to beta, and the sensitivity, or the true positive rate, is equal to the power, which is A over A plus C. This is sort of just a side note. Whenever you're looking at study analysis, someone asks you what's the alpha, what's the beta, what's the power, and these are things that you decide before the study begins. And so they're not diagnostic tests, it's just looking at it and making a comparison between sensitivity, specificity, and things that you look at in other study designs, which are the alpha, the beta, and the power. The last thing we'll look at is something called the receiver operating curve, and this is just a tool to use to compare two tests to each other. So you may have a test where one has a slightly lower sensitivity, but it also has a slightly higher specificity and stuff like that, and so you want to know which test is overall, which one's better. And so in World War II, whenever they're testing radars, they came up with something called the receiver operating curve, or ROC. And this is where you take the true positive rate, which is basically the sensitivity, It is the sensitivity. And you compare it to the false positive rate, which is 1 minus the specificity. Right down the middle, you get the line of no discrimination. And then, so whenever you move in this direction, it means your test is better. When you move in this direction, it means your test is worse. So you may get a test that whenever you plot it, it comes out to something like this. And then you may get another test that when you plot it, it comes out to something like this. And so you want the test that has the most area under this curve. And the more area under the curve, the better in general the test is. Now, something you don't need to exactly know, I'll talk about likelihood in another video, but whenever you take and you find the derivative of the slope, the derivative can be used as a good estimate of the likelihood ratio. And so by taking the derivative of your slope, you can also find the likelihood ratio and tell how good the test is from that. But typically, whenever you're comparing two tests, if a receiver operating curve is given, then the better test on the receiver operating curve is the one with the most area under the curve.